Hello, everyone, and welcome to the third session of our Spring 2026 program for the Virtual Inter-University Symposium on Infrastructure Management. For those of you who are new to VISIM, this is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today we'll have two presentations. Ayush Pandey will be presenting his work on economies of scale in ride pooling, with a case study of ride pooling in New York City. Afterwards, Victor Okoth will be presenting his work on the effects of vehicle spatial temporal arrangements on traffic flow. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat feature, and I can read them out loud. I'd like to point out that this meeting is being recorded and will be made available shortly after. Thank you all for being here today. And with that, we can start with the first presentation for today. I'm going to introduce Dr. Ayush Pandey, who is a postdoctoral scholar at the Larson Transportation Institute at Pennsylvania State University. He received his PhD from the University of Illinois at Urbana-Champaign in August 2025. His research focuses on transport economics, public transportation, congestion pricing, and causal analysis. Ayush, whenever you're ready, you can share your screen and you can start your presentation.
Yeah. Hey, thank you for joining, everyone. And yeah, Pablo, thank you for the introduction. So yeah, I'm going to present some of my work on scale economies and the decline of ride pooling. And then to make my case, I use data from New York City, but I think it's, the results should hopefully be more general than that, but we don't have data from everywhere else. So yeah, I guess everyone here knows what ride pooling is, right? It's services like Uber Pool that these companies like TNCs like Lyft or Didi, they all have. You can like when you need to make a trip, you can match with other people going in the same direction, and then you have small detours, but then to make it worth your while, they maybe give you a discount, you have a slightly lower fare, and yeah, it's just another service offered by these companies like Uber, Didi, and Lyft. And the key kind of like the key feature of these is that the passenger suffers like an extra detour, maybe extra waiting time, something like that. You have to suffer, but overall, it makes the system more optimal. It's better for the company to match trips going that way, and you don't have just one person in the car. So these services were launched in 2015, actually within a day of each other, and then they grew very rapidly. So once they were offered, I think they had a lot of backing from private credit, but these were also new services. They're more environmentally friendly, they're more sustainable. So they grew very, very rapidly until, let's say, early 2019. And they were by like even in 2018, 2019, both Uber and Lyft were offering new variants of their services like Uber Express Pool, where you walk instead of a car coming directly to you. You walk, and then again, it's like a matching problem, and your system is slightly more optimal because you reduce your detours. So it had a lot of attention. It grew very rapidly. Everyone was very excited about it. But then when the data from New York started coming in February 2019, they passed a law that they have to provide trip level data. And then that data started coming in 2019. And we see like a slightly different picture for these pool trips. So on the top left here, is my like cursor visible? Is it? It is, right? Yeah. Okay, so we see here like solo trips where there is no matching, which is like the bread and butter service provided by these companies. They follow a trend, they were going up, then this decreases during COVID, and then they're back on track. But if you look here at shared trips, they were already decreasing in 2019. They reached their peak around end of 2018 and 2019. From some auxiliary data, we can like kind of see that. But then they were already decreasing in 2019, and then they reach like a steady state, and then COVID hits, and then they go to zero. But then after that, they never really recover. So first on like this decline in 2019, it's almost all because of Uber. Lyft was still increasing, but like our hypothesis is that this happened because they wanted to have an IPO, and it was very expensive to keep subsidizing these trips. So what they did is they restructured basically their pricing strategy for match trips. So if you see in early 2019, they're losing as much as like $4 per unmatched trip. And then per week, they have like 400, 500,000 unmatched trips, right? So they're losing a lot of money. Even on match trips, they were losing $2, $3 per trip, even when they successfully match you. So it was just like they just lose a lot of money when they're doing it. And then, like I can calculate this because they give you fare information, but they also give you how much the driver made. So it's basically the difference of what the passenger paid and how much money the driver made from it. And only Uber has reliable data on it. Lyft's data is somehow like messy. You can't really like I can't make these plots. But then like around April, March, June, they kind of go into the break even point, and then there's some noise after that, but they stay around the break even point. And then the idea is that they both Lyft and Uber had their IPOs around March and May of 2019. So they were already kind of they were moving away from this private credit, and they had to decrease their discount. So that is kind of like the first thing of the initial decline in 2019. But even if you look at the decline in 2019, it's nothing compared to what happened after COVID. So all of these were shut down during COVID, and then they try coming back up, and they all come up like in late 2022, like middle of 2022, and you see a small rise here. Uber comes back in New York before Lyft. Lyft come back in late 2022, but then Lyft exists for a few months. Like Lyft is offering it for a few months, and then it stops offering any shared trip. So if anyone a few, I guess in Chicago, Lyft is quite popular. If you go to the Lyft app, you won't have the shared option, or I think not, right? And yeah, they shut down all their shared offerings. So these were very popular. They were about like 250,000 trips a week before COVID, and then they come back, and just in a few weeks, they could not sustain the system. So there's this decimation of the services, and if you look at the number of match trips, it's even worse because like at the peak you have like I don't know like a million trips per week, but at the end of it you barely have 100,000 per week. So all these pooling trips started in the United States and they've practically gone away. Only Uber offers them now. Lyft doesn't offer them, and even for Uber the discounts have gone down a lot. And yeah, the system is like it doesn't really exist as a viable offering, I believe. And you see like a similar story in match rate is during the decline, their match rate was still sort of consistent. Like it was going down, but it didn't go down by as much, like how given the scale of decrease in shared requests. And then when we see after COVID, like there's an initial period where the match rate is going up, but then it kind of gets steady. And then it increases again towards the end of 2024. But I'll talk about that later. They're doing something different there. They're kind of like changing the spatial offerings to increase the match rate, but the number of requests and the number of match trips are both going down in 2025. And I have like more data from 2025. I didn't put it here because it's just similar trends, but it is still going down. So shared requests and shared match trips are still going down in 2025. So there's this phenomena where we had this offering that was very promising, very sustainable, and it just sort of went away. So we were talking about why might it have gone away? And our hypothesis is that these systems have something called scale economies. So when there are a lot of people willing to match, you will make better matches, right? It's very like it's kind of an obvious thing to say. Any analytical model, any simulation models about pooling you look at, they all assume, or if they have like agent-based systems, these emerge out of them. You have scale economies is when you have more people matching, your matching gets better. And better as in you have lower, smaller detours, you can offer higher discounts because it's saving more money for the company, and then you're matching more trips. So our hypothesis is that this system has scale economies, and when you have scale economies you can have multiple stable equilibria. So just assume like some demand supply relationship and they intersect each other, and then when these are not like usually your demand would like increase and then your supply is decreasing, and they would have one intersection point. But when you have scale economies, even your supply gets better as the demand increases. So you could have multiple stable equilibria, and with vastly different values, which we see before and after COVID. It is, they differ by an order of magnitude. So our idea was, can we show that these right pooling systems have scale economies when we account for endogeneity in the system? So it is very hard to estimate if a system has scale economies or not, because what I'm saying is that if there's like a supply curve and a demand curve, I'm kind of making the claim that the supply curve has a positive slope. But it's very hard to show that because I only see the intersection between the supply and demand curve. So if with just this information, I cannot show that, like, I cannot estimate, I don't have enough information to estimate any of these values. So what we look at is some exogenous change in demand. Like what we have to look is some exogenous change that maybe move my demand curve while my supply curve stays the same. And then I can do some like math to figure out what the slope is. And then when you do the math, you figure out it's actually like the IV estimate. If you use your exogenous change as an instrument, it's the IV estimate. It's a pretty standard econometrics technique. I believe a lot of you would be familiar with it. So that was the goal, to show that there are these scale economies in the system. And then I'm using data from New York City. This data is all like, it's trip level data only available from February 2019. So I can't look at trips before that. And then to make like, because like if I have to calculate detours and stuff, I have to look at OD pairs to make it computationally tractable. I look at like top 50 OD pairs, but we also tried it with different combinations and the results hold. So it's just top 50 OD pairs so that we have more signal and less noise. And then my sources of exogenous variation are like precipitation. That was the first one we went to, is when it rains, it's very likely that you would, maybe call an Uber or Lyft. And when there's an increase in demand for Uber and Lyft, there would be a increase in demand also for shared trips. So that was like the first source of exogenous variation. And then here we show that it is a good source of exogenous variation. It does a good job at predicting the number of requests, and it is positive. The demand goes up when it is raining or snowing, basically, right? And then next we have like how do we measure the quality of matching? And there's, if we know what the TNCs were optimizing for, we could just take that objective function. But here we look at like the discount that is offered to trips that were matched. We can look at detours. So the discount should be higher, the detour should decrease, and the match rates should increase, right? And then, it's just how we calculate discount. We calculate it for an OD pair, we normalize it, and then we take the average for the whole system. But when we look at it, we can see that the discount is increasing with requests, but it's not a causal. Like, this is a correlation. It could be that requests increase when you offer higher discounts. So again, and one observation we had from 2023 is when we plotted the data, the discount was kind of steady around 20%. And then if you go to their media page, they show that it is 20%. So they hit their like targets very, very well. But when we look at discount, we find the IV estimate. We find that actually they're not changing discounts with demand. Like, it might look like when we look at the correlation that the discount is increasing, but when you actually do the causal analysis, there is no statistical effect relationship between the two. So that's the first one. And it's sort of expected. Same thing with detours. When you look at the effect of demand on detours in 2019, there's a slight negative relationship, but in 2023, there's none. And we do not see any like causal relationship between demand and detours and discount, which makes sense because what they're probably doing is they're setting it at a given value, and then they're trying to maximize match rate. So when the demand changes, your discount and your detours do not change. It is your match rate that is changing. So when we start looking at the match rate, we see, it has a positive trend. But again, is it causal? And we show it, it is causal. We can do IV estimates, and it's much higher in 2023 than in 2019. And it is statistically different from like the OLS estimate. OLS estimate is like a much smaller value. And then we can go ahead and do all sorts of robustness checks. and it always holds. And then we can try different instruments. Like I was looking at what happens when there's like games at Barclays Center. That is also an increase in demand. And then, we can just repeat the analysis and it shows that it is consistently positive estimate. Same thing, I look at the entries to subway stations. It is all like constantly statistically significant and positive. So we show that there are like these strong scale economies. And that was kind of the goal of it is probably a good explanation for why these services went away. And we also find that there's no effect on your discounts or on detours. It is all showing up in the match rate. So that was kind of the study. And then there's of course a lot of challenges in doing it. Like these zones are large, so aggregating data, like it's pretty challenging to aggregate that data together. You have a lot of noise. Calculating detours is very, very challenging when we go ahead and try to do this. The other challenge is that these TNCs constantly keep changing their strategies. Like we cannot get like a clean enough sample to actually do this like for a very long time. So for now in Uber, their number of shared requests are going down, their number of shared match trips is going down, but their match rates are going up. And I think they're doing like a spatial rebalancing of how these happen. But like in our study, we don't look at the spatial aspect at all. And then another change I saw in the last 6 months, Lyft has started offering like shared trips again. It is nowhere on the media page. It's nowhere on the internet. But if you look at the data, they have like very small number, like 100 trips per week in New York City that are requested to be shared, and like 6 or 7 of them are actually shared. So it's a very small number, but it looks like they're like changing their strategy again, which makes it even more challenging to kind of do these types of causal analysis. And yeah, we just like I should wrap up this paper, but yeah, we just have like there's a lot of analysis of very rich data sets. We find all types of like interesting things. At one point, we find that for a few weeks, Uber changed like their pricing formula to just jack up the fare per mile for match trips, and it showed up very clearly in the trip length of match trips across that period. So it's a interesting data set, and we find like a lot of like interesting stuff. Yeah. So yeah, I'm open to questions, and that's all from my part.
Thank you. Thank you so much, Ayush. That was a
Yeah,
wonderful presentation.
thanks.
So let's open up the floor for questions. Anyone who wants to ask, you can just speak up or write it in the chat and I can read them out loud as well. Any questions for Ayush?
I'll ask a question.
Go ahead.
Ayush, thanks for the presentation. It's very interesting. I'm curious when the ride share, when the polling goes down, do you have any idea whether there is like a substitution? Like where do all those people go? Are they just happy to pay and take solo trips? They move to some other modes? If you have any insight into that,
Yeah.
including
So
guesses. Yeah.
yeah, I don't. So from the data, I do not like. There's nothing in the data that I could conclusively look at, but my idea would be that I would guess it would be towards the subway, but also could be solo for short trips. So I looked at a lot of like what their pricing formula is, like a linear function of like a fixed, and then there's like a price per like minute, and there's a price per mile. And for shorter trips, it's not worth taking the mass trips. Like the pricing formula really penalizes the short trip. So my idea would be for shorter trips, which is a lot of trips like around Manhattan, where most of the demand is, they might have just gone to solo trips. It is very hard, however, to recover this from the data because like the number of solo trips and the number of shared trips differ by like an order of magnitude or more. So even if that shift happened, it would kind of just get lost in the noise in the data. We were trying to see if we could recover it. We are also trying to see if we could like see something with the entries to the subway station when this happens. But there's so for 2019, the data is strange. It's a small period. It's like slightly less than a year, and then there's a sharp decline. So it kind of hides like a lot of phenomena because the pricing changes so drastically. Uh, So that's like harder to kind of do things in a steady state. And then from 2023, we have like now a few years of data, like 2.5 years of data, but there's so few shared trips that it's very hard to infer anything from the post-COVID data. So that's why it's a little challenging. But I would guess for shorter trips, they're probably going to solo. And then for longer trips, it might be subway trips, because a lot of the most common OD pairs are these slightly poorer. I don't know, that's probably not the correct word, but like, not as the average income in those zones is not very high. When we did like the OD maps of where these trips are coming from, the shared trips are coming from, those are residential zones, going mostly to workplaces. And the average income in those zones is not very high. Another place where they have very high number of trips, where I think there is no change, is zones right next to airports, because I believe a lot of people park their cars at those long-term car parks, and they just take an Uber. And because they're close by, they probably take like the pool option, because they can guess that they probably will not be mashed. So I don't think there's a lot of change here, but I think we'll see a lot of substitution in the residential zones. Yeah, thank you for the question. I hope I answered it.
Thank you, Ayush. I think Adarsh, you have a question?
Yes, sir, I have a question. Do you think do you think the do you think the share riderships will depend on the land use pattern? Because because uh, because uh, because I belongs to India, I usually see that when the people move to the office sites, they prefer more share ridership as compared to the recreational area. So, so my question is that how the share riderships will influence the land use pattern.
Well, okay, I couldn't hear the first part very well, but I heard the question, which is how will shared rides impact the land use pattern? And I think it will not. It's a very small amount. If you look at the amount of like money Uber makes or loses from it, or if you do like any kind of calculation, I think it's a very, very small fraction of it. And I don't think shared rides by themselves is gonna have any effect on it. Another like way to kind of like away from New York to kind of prove that is Chicago has data on the amount of tax they collect from these TNCs, because they have the ground transportation tax in Chicago. And you can also look at those numbers, and it's a very small amount for the city of Chicago. So it's shared trips. I think at the moment there's very few, and then we're not seeing any signs that it would go up. So I doubt it would have any like meaningful effect on land use or something. If I understood the question correctly, that would be my guess. Say,
Okay, thank you.
yeah.
Are there any other questions for our speaker? Well, if not, thank you, Ayush, once again. That was an amazing presentation. Thank you, Victor and others as well, for your questions. And with that, we can move on to the second part of today's session. So I'm going to introduce our next speaker for today. The next speaker is Victor Okoth, who is a PhD student in the Transportation Systems Analysis program here at Northwestern University, where he is advised by Professor Mark Goni. His research is on characterizing scatter in fundamental diagrams, higher order hydrodynamic traffic flow theories, and traffic forecasting using machine learning, reinforcement learning, and classical time series models. Prior to Northwestern, Victor was an instructor in the engineering program at NYU in Abu Dhabi. Thank you, Victor, for joining us. And when you're ready, you can just share your screen and you can start your presentation.
I can share this.
I think that's good. Perfect.
Okay. Can everyone see my screen?
Yeah.
All right. Thank you so much, Pablo, for the introduction. Hi, everyone. As Pablo said, my name is Victor Okoth, and I'm going to be presenting on this title, Unpacking Density, Investigating the Effects of Vehicle Spatial Temporal Arrangements on Traffic Flow. This work was done with my colleague, Nachuan Lee, and our professor, Hani Masani, who passed on last year, unfortunately. God rest his soul. Yeah. So what is unpacking density about? And this slide is really a summary of everything that this presentation is about. And the idea here is that if you see on the left, you see a speed density plot, and you can see that for any speed, you have multiple, well, for any density, you have multiple speeds. And for any speed, yes, you do have multiple densities as well. And this has been a thing that's been observed by multiple people that are looking into this. However, when you model these, generally, you just fit one line, and therefore you match each speed, rather each density to one speed. So on the right, we then have the same speed density plot, but here we are kind of segmenting these points by by a measure. In this case, we call it entropy. But entropy really is supposed to be a proxy for anything that differentiates speeds at the same density. And we think of this as really the arrangement of trajectory points in a space-time graph. To motivate this, it's something that it's kind of inspired by, let's say, material science or physics, whatever, where the arrangement of atoms in a body is kind of supposed to affect its properties. So similarly, we say that if you're taking a space-time area and you're calculating ED's definitions for speed, density, and flow, those gross measures are not enough to describe the characteristics of that traffic. You also look at the arrangement of particles inside this space-time area. Yeah, so this is an outline of the presentation. We say the problem we're addressing is one-to-one speed density relationships that do not sufficiently show the relationship between speed and density, or just the speed of traffic. And then a little background on previous work that has been done on this area. And then we'll look at the data, how we process it, and introduce entropy, which is this one measure that we found to really characterize the spatial temporal arrangements. And then ideas on how to model entropy into the speed-density relationship. And then I'll close with summary and ideas for further research or some other things that I've been doing since I found entropy. So this is previous work. I can't go through all of it, but to go, I guess, just the main ideas. So this is observed by Khan and Rebon, who said that instead of having these ideas on like an equilibrium speed density relationship, what you really have is a speed density plane at which you can have multiple speeds for any one density or multiple densities for any one speed. And so he really criticized the idea of an equilibrium speed density curve. Then the other theme that I think is useful in this study are these other ideas on what explains the variation, right? And so there's composition-specific fundamental diagrams, for example, where it's like if you have cars or trucks or buses, etc., that will kind of explain part of that segmentation. And you have like different studies to try to segment this. An idea that I found really interesting, and this was by Mohan, I think most of this work really comes out of India, is this idea that there is two measures that describe how fast you go. So there is concentration, which we would let's say, when you see the speed density plot, is that as the concentration or density increases, your speed definitely goes down. And then at any given density, there's opportunities to either go slower or faster. And so they kind of split this to name one concentration, that's like density as we know it, and then congestion to be able to kind of limit how fast you can go, given that there is a specific number of vehicles on the road. And if you have like traffic that does not necessarily obey like lane patterns, or you have mixtures of different vehicle classes, this kind of thing is, I think, pretty easy to imagine. And then you also have all these different traffic flow models that include terms that are not just density to model speed. This is, for example, looking at density gradients or any other look ahead pressures, things like those, I think fit into this idea that for a given density, you can have multiple speeds. So for the data that we use for this study, it's from I-9094 and I-395. You can see these on the left and the right. The I-9094 is taken from like the west of Chicago, where the I-90 to O'Hare Airport and the I-94 to Wisconsin diverge. And the I-395 is taken from Washington, D.C. And at the bottom left and bottom right, you can see simplified representations of these geometries. I-9094 has 6 lanes in total and covers about 400 meters and 800 seconds. I-395 has 3 lanes and it covers 400 meters as well and about 7,000 seconds, so it's more extensive. And then the calculations for distances and speeds are not that difficult. We get them from ED's definitions, which I hope people have taken like some introductory traffic analysis classes. What's different here, though, is that we shear map the trajectories. And what that means is that we add to each time a shear factor, which is, let's say for each x position, you divide by this omega, which is a shockwave speed. So the effect of this shear mapping is that the shockwaves appear to propagate parallel to the distance axis. If you can kind of see this little diagram here. And so that allows you to kind of, it's like when you choose these space-time areas, you're choosing areas that are kind of similar to each other in a way. So you can see this kind of visually. And then when you calculate the densities and flows and speeds, they must ultimately be like ED's real definitions. And so you have to, in a way, do the inverse operation so that you transform them back from their shared quantities to the unshared quantities. And this is how you do that. And now I'd like to talk about entropy, which is an idea that you know, or you've probably heard of. Mostly I guess the most common ones are Shannon entropy and Boltzmann entropy. And I'll start by talking about the Boltzmann entropy, which characterizes the arrangement of particles in a multi-particle body. This is something that you probably study in physics at some point or chemistry. But the reason that I talk about it is to motivate the relationship between what we're trying to do to other areas where you try to differentiate, whether to use the arrangement of particles in space to discover the properties of a given body. But for the rest of this discussion, when I speak about entropy, it will be the Shannon entropy, which characterizes how evenly points are distributed in space. It's something that has been used in lots of classification applications, and this is really fundamentally a classification application. For example, it's been used to categorize urban traffic as orderly or disorderly, to characterize the similarities of trajectories, to characterize track stops for different, like by purpose or the evolution of noise, turbulence, and other phenomena. And for our purpose, this is how we calculate it. So here you have a like space-time area over which you can calculate ED's definitions as we explained above. And then to calculate the Shannon entropy, you split this area into multiple cells. This is a simplified example in which we have just 4 cells. And then you get the proportion of trajectory points in each cell and use that as a probability. And then you apply this entropy formula. So you multiply its probability by its log and sum them and take the negative of that. You have to be careful in doing the cell size selection. What we think of is that each space-time area really represents, it's like a set of photographs that you take one after the other. And so we're thinking about, if you imagine like a set of photographs just kind of like laid next to each other, they represent still pictures in a way. And so what we try to do is to find the cell size such that there is no movement. It's as if you're looking at like a series of still pictures just slapped next to each other. And so we choose 1 meter and 1 meter and 1 second for this. We kind of do some kind of sensitivity analysis, like playing with different cell sizes until we find the point at which distance-based entropies, like where you can calculate distances, just disappears. And then you have the like the clearest segmentation, even though you can do distances as well. So this is what it ultimately looks like. I-9094 and I-395 at the very top. This represents all the densities. I-9094 is pretty congested, and I think entropy works very well when like differentiating congested areas. For I-395, you can also see the separation, but it is not as clear. However, once you take out the free flow areas and you just look at the congested regime, you can see the segmentation upwards, like vertically. You have like lower entropies at the bottom, and then like the entropy kind of increases as you go up. Then the other thing that I'd like to look at is to really go down into like zoom into specific space-time areas that have the same density but different speeds, and kind of see what they look like inside. And we see that these are just examples. The ones on the left, which would have high, rather lower entropies, are kind of like the driving is more heterogeneous. And I think that's kind of what entropy captures in this. There's like less accelerations on the left, rather on the right. It's just almost straight lines throughout and pretty evenly spaced. Not as many lane changes. So I think this might just be different driving behaviors that cause this, that cause the heterogeneity, which ultimately I think is what entropy is capturing. So now we move on to ideas to model this entropy into the speed and density relationship. And you can use any, but we're just using a modified green shield. You can use green shields or green bar or any other model, really, as long as you find consistent way to interpret it. So this model has the following important parameters. You have V naught, which is the minimum speed at which traffic keeps flowing very slowly, even at congestion. And then you have the free flow speed, which is a physical characteristic. I like it because of the speed intercept, VF, which does not necessarily have a physical meaning, but it's essentially like if you, like how fast would you want to go if there was no constraints or some kind of perceived free flow speed. And have this exponent alpha, which shows how quickly this graph would would decay as how quickly the speed would decay as density increases. So this is it. And so what we do is we have a baseline model where we're fitting our data to using that equation. This is just speed and density, and this is kind of what that looks like. You can see the parameters for V naught and VF, and importantly, the R squared. So the variance that this model would explain is about 78% in the baseline case without just speed and density. And then the question is, how do we account for entropy? One idea that we had was to cluster by entropy and then just fit the baseline equation to each of the clusters, right? And so this is kind of what that looks like. For these, we calculate, so for each cluster, we calculate a R squared value, and then we find a global R squared for the entire clustering operation. And we see that for I-90, the R squared is 82, so that's an increase of maybe just 4% explanation. For I-395, it's 89. That is almost an 11% change in variability explained. And then this is a different way to think about integrating entropy into the equation. So what we observed we got this insight from the clustering, which is what came to our mind first, that the entropy might be influencing the VF and the V naught, right? And so we model the V naught and VF as linear functions of entropy, and then just substitute them into the equation altogether. Then try to do that. I should note that with F-tests just showed that the clustered model was much better, rather was significantly better than the baseline model. And then this entropy enhanced model we just explained how we formulate it, and then we fit it to the data. And these are the results that we get. For the I-9094, the R squared just goes to 98%. It almost just explains all the variability in it. And for the I-395, which is the one that has the free flow, it's not really as congested. We explain about 92% of the variability in there, which is still pretty significant increases. So this is how that works. And the entropy enhanced model also, like F-test showed that it was better than the baseline model. But what we thought was interesting is that this entropy enhanced model is not significantly better than the clustered model. And we thought that was a pretty interesting result. So you choose one or the other. And then we're thinking about how to interpret for the entropy enhanced model, you then have multiple combinations of V naught and VF, right? And we think as we said in the beginning, they kind of indicate be like impedance in a way. So given that you're limited by density, how fast can you move, or how slow can you, what's the minimum and what's the maximum? So we found the minimums and maximums for these trajectory data sets, but there's many different combinations in between. And so different drivers would then be able to take advantage or not take advantage of opportunities to go faster. So I've spoken a lot about entropy, partly because that was the first successful measure of spatial-temporal arrangements. But the key idea is that it is the arrangements themselves. So any other measure that can accurately characterize the heterogeneity in a space-time trajectory graph would do just as well. And so I continued looking, and I found this other measure called lacunarity, which is pretty much related to entropy as well. But what is different or interesting about it is that instead of calculating it as such, as I explained, like doing a physical calculation, I thought that an interesting way would be to simply plot the space-time trajectories and then use like image analysis techniques to calculate that. So I'll find a script, essentially take a picture and feed the algorithm the picture, and then get a measure of lacunarity, which also measures how it's like, think of it like texture. What's the texture of a picture, and how are points clustered within that picture. You can also kind of measure it, I guess, if you think about the coefficient of variation, so the square of that's like very, I guess, in the easiest possible definition, that's kind of like the mathematical measure for lacunarity. And it kind of does the same thing. In fact, it fits, I think, even better than entropy. So you've seen the clusters, so I don't need to go over that again. And that is especially for the enhanced model, like it almost predicts all the points, but I think for higher values of speeds, it underpredicts. That may be because we chose a linear relationship for the like V naught and VF, or maybe some other reason, but we think that is interesting. So to summarize, the key point is that we think that spatial temporal arrangements, and any measure that can really capture this, because there's like, if you think about it in a discrete form, there's so many of them. So some proxy that can give a numerical figure to how things are arranged in space-time to differentiate speeds at the same density. The limitations of this work is the trajectory resolution can limit the how accurate you can go. And there's obviously missing points in image-based extraction techniques. There's ideas to use distance and time-based entropies, where for each like little subcell, you calculate the time and then look at the proportion of time or distance in a given cell to do the entropy calculation. So future research is thinking about how driving maneuvers change or are affected by these spatial temporal arrangements. Other measures of vehicle spatial temporal arrangements that do have a significant effect. For example, lacunarity, which I just spoke about. And then how entropy affects other traffic phenomena, like is there a relationship between traffic breakdown and recovery, hysteresis, and these other things. And then estimating entropy in real time, because but what can you do with it if you can't estimate it? And I think this is where the lacunarity measure came in. Like if you can take it directly from a video or a camera, that might be an interesting way to go about it. And then to find other measures. Maybe you can find something that will just give you 100% and explain the rest of the variation that density does not explain. So that is it. And I'll take questions and suggestions because it's ongoing work, and anything that can help to improve it is very welcome.
Thank you so much, Victor. That was another amazing presentation. So now, like Victor said, if anyone has any questions for him, we can take a couple questions before we finish the session. Any questions?
And suggestions.
Suggestions as well. You can write them in the chat or just speak up if you want to. Go ahead.
Yeah. First of all, thank you so much for the great presentation, and we have discussed a bit about your work. But what do you see as the next step, and who do you see utilizing this good work that you did, like an agency like IDOT, someone from the industry, both. So if you have an insight on those next steps and dimensions, perhaps.
That's a good question. I keep vacillating between whether this is useful at all or it was just like some interesting theoretical exploration. But I think that it can have applications on like capacity analysis. It was someone that a reviewer just sent back. It's like, this is something that you could use to do capacity analysis or to look into traffic breakdown. Traffic breakdown is something that so many people are interested in. And so that's something that, for example, like different agencies that are trying to figure out how to prevent, how to control traffic in such a way that it doesn't break down or recovers quickly, or even transport companies that want to figure out how to avoid traffic if they can be able to predict where they're not going to get stuck. That's an application. But in terms of next steps, I guess I'm thinking about the work as like leading into my thesis. And so this is unpacking density 1, which lays out the ideas, and then unpacking density 2 to look at applications, and unpacking density 3 is to think about how to integrate this like multi-valued fundamental diagram into dynamic traffic flow equations. Think of like LWR, which essentially uses the baseline fundamental diagram. How could it work with a multi-valued one? So that's the, and then ultimately how to actually solve the equations. If I can prove that, if I can find that the multi-valued fundamental diagram does predict like traffic flow in space and time more effectively than using, let's say, LWR with just a single valued fundamental diagram, then that would be, I guess, a capstone to this work. Yeah.
Thank you. And it's really super interesting, and I think it's super useful as well. And you see it from comments and your ideas already. So great job, and thank you for answering the questions.
Thanks.
Thank you, Vasilis, for the question. Are there any other questions for our speakers?
Oh, yeah,
Ayush?
I'll go ahead. Yeah, I already had a question where you put it in future work, but I think like great work. Thank you for the presentation. I feel it would be, because you're asking for suggestion, it would be great to look at like hysteresis, the role of acceleration, deceleration, and the entropy measure, because of the profiles you showed. It shows something like that happening. Like I think from the Treiter and Meyer papers, and then after that a series of literature that followed with that. I think that would be very interesting if you connect the two, because like there they explain the hysteresis, but how do you measure it? So this might be like a very good measure of it. So yeah, that would just be my suggestion.
Thank you.
Yeah.
Any more comments? I think we have time for one more question if anyone wants to ask Victor anything else. If not, we can conclude today's session. I want to thank everyone for being here, everyone who asked questions and interacted with our speakers, and a special thank you to Ayush and Victor. It was an honor to have your presentations today at VISIM. And I hope I will see all of you on our next session, which will be the last one for the spring, where we'll have the final 2 presentations for the series. And with that, we conclude the session. Thank you all, and I'll see you next month.
Thank you.
Thanks,
Pablo.
Thank you.